Hello, I'm James Wotton of IBM Quantum, and here is another video on Hello Qiskit, which is a set of interactive exercises that lives inside the textbook Learn Quantum Computation Using Qiskit. Now, in this video, we're going to look at level 2, basic single qubit gates, and of course, in the last video, we looked at level 1, which was about bits, because quantum computers, just like conventional computers, are built upon the idea of bits and manipulation of those bits. So we need to get into the mindset of using and manipulating bits before we can continue. That's what level 1 was all about. And it was also about introducing the visualization that we use in this game so that we don't have to use any linear algebra, at least in this particular context. So in level 2, we're going to be looking at the quantum version of bits. We're going to be thinking about how they differ from normal bits, and we're going to be looking at some of the most useful and well-used ways of manipulating them. Okay, so let's begin. This is a qubit. We have one qubit, and we have one thing that we're allowed to do to it, which is called an X gate. So let's do it and see what happens. That black circle became white. Oh, sorry, the white circle became black, but now the black becomes white and then goes back to black again. That has some similarities with the first exercise of the first level, where we had a single bit and we had the NOT gate, which flipped its value. But the difference here is that instead of having a single circle representing a single bit and the colors black and white represented whether it was 0 or 1, now we have a single qubit represented by 2 circles. And the reason for that is that a qubit is a bit different to a bit, but it also has similarities. So the similarities are that it is truly a bit. It has 2 possible states to it. So a bit is something that has 2 possible states, whether you call them 0 or 1, or true and false, or yes and no. The important point is that there are 2 of them. When you look at it, it's doing one of 2 possible things, and that's all it can do. That is the defining feature of a bit. And the same is true for a quantum bit, a qubit. The difference is that we have more ways that we can ask a qubit what it's doing. For a normal bit, we can just look at it and see if it's 0 or 1. That's all we can do. With a qubit, there's multiple ways that we can phrase the question, are you 0 or 1? And these different questions, these different ways of extracting that information will yield, in general, different outputs. However, you can't ask both of them. You can't extract one of those pieces of information and then just go and extract the other one without any consequences. If you could, you would be getting 2 bits out of a qubit. And if you could get 2 bits out of a qubit without suffering any sort of consequences for that, then it would be a quantum version of 2 bits and not a quantum version of 1 bit. And so the reason why it is really just truly a quantum version of a single bit is that you have to choose which of those 2 questions you ask. And after you've asked the one that you ask, then you can think of it as essentially the qubit has been destroyed, or at least it has been disturbed beyond what it was previously, so that it doesn't make sense now to go and ask the other question, because you won't get the same answer that you would have done. So there are more than one way to extract a bit out of a qubit, but you have to just choose the one you're doing, and that event will change what the qubit is doing accordingly. So it's not just like looking at a bit and seeing what value it is, which is a completely passive process. The act of extracting an output from a qubit is an active process, and therefore it has a name. That event has a name, and it's called measurement. Okay, so 2 different ways that you can extract a bit from a qubit are called an X basis measurement and a Z basis measurement, or a Z basis measurement if you insist on American pronunciations of things. Now, the names behind these are not something that we're going to dwell too much on. It's just that there are two of them and they have different names, and their names are X basis measurement and Z basis measurement. In this visualization, Z basis measurement is represented by the bottom circle and X basis measurement is represented by the top circle. In this case, we see a qubit, which if you do a Z basis measurement is definitely going to give you the outcome 1. And if you do an X basis measurement, it's going to give you a random outcome. And that's just because we use a black circle for 0, a white circle for 1, and a grey circle for a random result. Now we are told in this puzzle to turn off the Z output. So we want the Z output to be definitely 0 rather than definitely 1. And that is done by the X gate, which is effectively the quantum equivalent of the NOT gate. Okay, let's move on, and we are going to get now another qubit. And this is a second qubit, so it's in a different place. Again, the lower circle represents the outcome of a Z measurement. The upper circle represents the outcome of an X measurement, and we again see a qubit which is definitely going to give us a 1 if we measure in the Z basis, but it's definitely going to give us a random result. Hang on, that's a bit of a weird phrasing. It's going to give us a random result for the X basis. We need to make it so that it's definitely going to give us a 0 for a Z measurement. It's exactly the same as before, just on the other side. So there we go. So from that, before now, whether it's been bits or qubits I've been talking about them as the one on the left and the one on the right. In future, I'm going to call them by more techie sounding names of qubit 0 or Q0 and qubit 1 or Q1. Qubit 0 is the one on the left and qubit 1 is the one on the right. Okay, now we're going to get a new gate to play with, and it's called the H gate. So let's see what it does. We have a single qubit. We apply the H gate, which is also known as the Hadamard. We apply it to that qubit, and we see that the two values have swapped places. We currently have a qubit which will give a random result for a Z basis measurement and a definite 0 result for an X basis measurement. But if we do the Hadamard again, those two swap. Now it's definite for the Z measurement, random for the X measurement. Do it again, it swaps back. It's just swapping these two things. That's all the H is doing. Okay, and also if we want to see the circuit that is made by solutions to the puzzle, we can run this code cell down here and it will show us these circuits. So here we see the circuit, which is of course for qubit 0 and qubit 1. And a circuit is basically a history of what happens to them told from left to right. So we see that they are qubit 0 and qubit 1, and that 3 Hadamards have been applied to qubit 0, which is exactly what we just did. Okay, so if the Z output is certain, as we've seen before, it flips its value. But what if it's random? So here we have the case where the Z output is random and the X output is definitely going to be 0 if we were to do that particular kind of measurement. We have to get the Z output fully off, not just random as it is here, but definitely going to give a 0. We can use the H gate as many times as we like, but we have to use the X gate exactly 3 times. So if we were just to shift the certainty over here and use an X gate to, well, we need it to be fully off, so that's what it was before, isn't it? It didn't accept the solution because we have to use the X gate 3 times. We can use it twice to turn it on and then off again, but we're still left with another time. And if we use another X, of course it goes on, which is not what we want. What we can do is put the randomness back here and perform another X, because when we have a random value here, it's randomly 0 or 1. If we flip that, then the 0 becomes 1 and the 1 becomes 0. So it's randomly either 1 or 0, which is the same thing. And the X has no effect on the outcome of an X measurement. You might notice that both the X gate and the X measurement have the name X. And there are reasons behind this. It's not just a coincidence. But for the purposes of these puzzles, you can just think of it as being that the X gate is the gate which flips the value of everything but the X measurement. And we'll come across a Z gate which flips the value of everything but the Z measurement later on. Anyway, let's do another H to put everything back where it needs to be, and the puzzle has been solved. Okay, in puzzle 6, we've seen that the X gate flips the Z output but not the X output. If we want to flip the X output, then we have a new gate which is the Z gate. So let's just apply a Z gate and see what happens. It flips the X output from white to black. We need to turn the X output off. That's what we did, so we can move on. Okay, now for puzzle 7. Turn on the Z output using the X gate. So let's run this puzzle. Oh, sorry, without using the X gate. So we don't have an X gate to play with at the moment. If we did have an X gate, all we'd have to do is use it. We could use an X gate, turn that Z output on rather than off, and we'd be done. However, we don't. And the Z doesn't do anything. It flips the random value. It has no effect on the outcome of the Z measurement. So this is not going to be of any use to us on its own. Now I'm just going to run this again to restart it. If you ever want to restart a puzzle, don't press restart, because that restarts the whole notebook and you have to go to the top and start importing things again. Just press run if you want to restart a puzzle. So what we're going to do here is, because the Z doesn't do anything, we're not going to do it. The only other thing we can do is an H, so let's do that. And now we're at a point where a Z does do something. If we apply a Z, it will flip that black to white because it's now in a place that the Z can reach. Now it's on, and we can use the H to put that back, and the end effect is exactly the same as if we had done an X. And that is one of the most important things about quantum computing, or any computing, that if you combine operations, you get other operations. You can combine the things you have to make the things you want. It's not usually that you combine the things you have to make something that you should have had, but a puzzle just arbitrarily didn't allow you to have it. But instead you're usually building up to a larger algorithm. But in this case we see that our circuit, an H, a Z, and then an H, gives us something which is equivalent to just doing an X. Okay, puzzle 8. You might have noticed that the X outputs are always random when the Z outputs are fully on and fully off, or vice versa. And this is due to something called Heisenberg's uncertainty principle. So it's something that you may have heard about, something that you may have seen web comics about. Comes in the form of quantum computing, in that you can't have definite certainty for the outcomes of these two different types of measurements. Because again, that would be kind of like having 2 bits stored in the same qubit, and then it would be a quantum version of 2 bits rather than a quantum version of 1 bit. So the restriction that you can only store 1 bit's worth of information inside a qubit gives us this this factor. If you have one of them completely certain, if you have the outcome of a Z measurement completely certain, then the outcome of an X measurement has to be random, and vice versa. Okay, so now make the X output be off and the Z output be random. We just have to do a Hadamard. Nothing very complicated there. This exercise was mostly just to give me a chance to tell you about Heisenberg's uncertainty principle. Another consequence of this is that it's not just that one can be certain and the other can be random, but you can also have the certainty shared among the two. For example, you could have a case where they are both random, but they are biased towards a particular value. In this case, we see that both of them are dark grey. So far, we've only seen black, white, and sort of what I might call middle grey, representing a completely random value. In this case, we have dark grey. It's random, but it's biased towards 0. If you were to ask for a Z measurement or an X measurement, what this qubit is doing, it's most likely to tell you 0, but there is some randomness, so it could also tell you 1. So both of them are fairly certain of being 0, but they're not completely certain. So we've kind of shared the certainty out here. So in this case, we have to make them most likely to output a 1 rather than most likely to output a 0. We can use the Z to flip the top one from being biased towards 0 to being biased towards 1. We can use an H gate to flip them around such that the Z gate can also do the other one. Of course, we could use a Z and an X if the puzzle had allowed us to use an X, but it didn't, to make everything a little bit more challenging. Now we get to see both qubits at once. So let's start off by just looking at both qubits at once. We're already very used to these two qubits, and having them both sitting there at once shouldn't be too confusing, I would hope. Qubit 0 is the two circles over on the left, qubit 1 is the two circles over on the right. And our job here is to make both Z outputs random. And so we can just do a Hadamard on both qubits in order to do that. So Hadamard there, and the Hadamard there, and they're both random. And this brings us to a point which is very similar to one of the puzzles from the first level, where those two bottom circles are grey, so they're both random, and we can ask ourselves, well, if we've got two qubits, two outcomes, the outcomes for the Z measurements of both qubits, and they're both random, well, what else might we need to know about that? Are they correlated? Are they anti-correlated? Or are they just completely unrelated, with any agreements or disagreements being random? If we want to know that additional information, we need something else on our visualization to tell it to us. So that's what we're going to see in the next puzzle. Oh, sorry, I should stop clicking that button. So here is the board full at last. Again, we have the two circles representing qubit 0 on the left in the squares with the light background. We have the two circles representing qubit 1 on the right, again in squares with a light background. And in the other four squares, we have four circles in the middle, and they are going to do the job of telling us about correlations. And the reason why we need four of them is because for each qubit we have two choices about how to measure it, X and Z. And so we need to know the correlations when we choose the Z measurement for both qubits. We need to know the correlations when we choose the X measurement for both qubits. We need to know the correlations when we choose X for one and Z for the other, which there's two possible iterations of. So that's why we need four of these new circles. So of the four new circles, the one at the bottom represents the correlations for the two Z outputs in much the same way as it did in level 1. So here, because they are both independently random, that one is grey, saying that there is no correlation at all between the Z outputs of both qubits. What we need to do is make the Z outputs certain to agree. So for one thing, we need to make them both certain. So let's do that. Now they are both certain, and actually I guess it's, we should make the Z outputs both certain to disagree. So they are both certain to agree at the moment because they are certain to both output a 0. So let's flip 1 to be 1 so that they are certain to disagree. Okay, next we move on to the next puzzle, and this is just going to introduce us to one of these other new circles, in this case the one at the very top. So we start off with a state here, much the same as where we left the last puzzle. The Z outputs are both certain. One is certain to be 0, one is certain to be 1, so they are certain to disagree. But what we need to do is make the X outputs certain to agree. Okay, so again, let's make the X outputs both certain of being something, and then they are certain to disagree because one is certain to be a 1, the other one is certain to be a 0. And now again we can flip one of those values to make them certain to agree. And that certain agreement between the two X basis measurement outcomes is represented by the circle at the top being black. So the circle at the top represents the correlations between the X measurement outcomes of the two qubits. If it's black when they are certain to agree, as in this case, white when they're certain to disagree, grey when their agreements or disagreements are random. Next we have the other two puzzles, which of the 4 new ones are the ones on the left and the ones on the right. And these are for the cases where we look at the X output of one and the Z output for the other. So you can think of the X output of qubit 0 as belonging to a certain row, and the Z output for qubit 1 as belonging to a certain row also. You can then look at where those two rows intersect, and the circle that lives there is the one that represents their correlations. So of the 4 new ones, that's the one on the left. And of the 4 new ones, the one on the right represents the correlations between a Z output of qubit 0 and an X output of qubit 1. I would love it if my streaming thing captured my cursor so I could just point, but it's also good to explain the meanings behind things as well as just using our very basic ability to point at stuff. Anyway, in this puzzle we need to make the X output for Q0 certain to disagree with the Z output for Q1. So let's make the X output for Q0 certain to make our job easy. And now the X output for Q0 is certain to agree with the Z output of Q1 because they are both certain to be 0, but we need to make them disagree. So let us flip, for example, the Z output of Q1, and we have what we need. Okay, puzzle 14. This is going to show a slightly more complex case where we don't just have one of the outputs being random and the other one being certain, but a sharing of the certainty. In this case, both of the qubits are biased towards 0 for their Z outputs and biased towards 1 for their X outputs, each of them being slightly random. For this, you can see that the correlation between the two Z outputs here is such that they are most likely to agree, because they're most likely, both of them, to be 0, so they're most likely to agree. However, that likelihood for the agreement is a little less than the likelihood that each of them are both individually 0, just because of the way probabilities work. Also, the X outputs are both most likely to agree because each of them is most likely to be a 1. And for the X output of one and the Z output of the other, they are most likely to disagree because of course one is most likely to be 0 and the other one's most likely to be 1. And these are represented by different shades of grey, which are going to be a little bit complex to keep track of all of these shades of grey, but we'll find a new visualization for when that becomes tricky later. Anyway, what do we have to do in this puzzle? We need to turn the two Z outputs on as much as we can. Currently they are both off, so we will do an X on qubit 0, and now we've made it so that the two Z measurements are most likely to disagree because one is most likely to be 0 and the other is most likely to be 1. And you might have noticed here that the effect of the X was to flip an entire row of circles. It doesn't just flip the one for the Z measurement of qubit 0, but it also flips all of the ones along the same row because they correspond to correlations with the Z outcome of qubit 0. So everything along that row gets flipped, and you'll be able to see that for the row that follows from the Z output of qubit 1 as we apply this next X. There you go. So try these things out a bit yourself and you will hopefully come to understand all of this a bit better. Now let's turn off the Z outputs in this final puzzle, and we can do that by making them both certain. They're certain to be on, they're certain to be in their 1 state. We want them to be certain to be in their off state. Again, we can see the effect of rows getting flipped, although it is a bit easier to see when we've got shades of grey. Now I must wonder, what is the point of this one? And it's in order to plug the hello quantum game, which is an app that you can find, and it's basically the same stuff as in Hello Qiskit, but it's less pedagogical. It doesn't have constant explanations as we have in Hello Qiskit, and it's more visual. So when you see an H implemented in this case, it's not just the values get swapped, but you actually see an animation of that swapping process. So the animations here do make it a little bit easier to understand some of these operations. You can also see the effect of an X on a row. So it may be worth checking out the app version in order to get some of these cool animations and make everything a little bit more clear. Finally, let us move on to the last, oh sorry, I thought there was another puzzle. There isn't. Next is level 3, where we start looking at 2 qubit gates. So we don't just have 2 qubits at the same time, but we do manipulations of them that are 2 qubit manipulations. Basically, it's going to be a 2 qubit version of the controlled knot that we saw in the last video. But that's going to be in the next video. If you want to know when it comes out, then you can like and subscribe, of course. You can also follow me on Twitter, or you can just keep checking back at the playlist where all of these videos live and see when it happens. So that is all I've got to tell you today. I hope you have a good whatever time of day it is for you, and I'll see you next time. Or of course I won't see you next. They always say that on TV, don't they? They'll see us next time. You can't see us. That's not how TV works. Anyway.